Today we're going to talk about atomic structure, why the atom is shaped the way it is, and how to read atomic symbols on the periodic table. Alright, the first thing I want to talk about is just the subatomic particles, first being the proton. I hope that you all remember that it is positively charged, and the nucleus. Alright, the neutron is also a particle, but it has no charge. It is neutrally charged, and the nucleus as well. Now, protons and neutrons, they are very close to about the same mass. It is measurable. Protons are 1.673 times 10 to the negative 24th grams, while neutrons are 1.675 times 10 to the negative 24th grams. And these are measurable amounts. This is not something I expect you to remember or memorize, but you do need to understand they're about the same size. Okay. The third particle is the electron. And I think you all remember that it is negatively charged. And it is a particle that is orbiting. Around the nucleus. Okay. Now, we know the mass of an electron, but it is so incredibly insignificant to the mass of an atom that we don't really care. We don't count it. An electron is 1,840 times smaller than a proton. So if you think about a basketball and a tiny BB, that's about the size difference between a proton and an electron. It is significantly smaller than the proton. So while we do know the mass of it, it's not something that we typically measure when we are accounting for the mass of an atom. Okay? Now, one of the people that we give credit to the atom is a gentleman by the name of Niels Bohr. And he is the person that proposed the planetary model of the atom. So what does that mean? What is the planetary model? Well, if you think about the planets orbiting around the sun, that's what our electrons do. They orbit around the nucleus. Okay? And he was able to explain this with the hydrogen atom. With a method of light scattering called spectroscopy. Now, we'll talk a little bit more about this as time goes on, but spectroscopy is using light frequencies to help identify elements. And he was able to show that you can change those light frequencies depending on what's happening to the atom. And he called it exciting the electron. So what he was able to show is that if we have our nucleus here and our electron orbiting the nucleus, okay, our electron is traveling around here. if we excite the electron and make that electron jump to another level, like would be a bigger atom, then that spectroscopy, that light scattering, changes on the atom itself. And with all of his lines that he was able to show and the levels he was able to show, he had in level 1 and level 2s, and he had level 3s, and he was able to show that you could excite that electron to different levels. Okay, and when the electron fell back down a level, that's when the spectral image would change. And while this was a very, very easy way to show what hydrogen looked like, it's very hard to show what other atoms look like, because once you get more than one electron, the movement of the electrons changes. So while we use his planetary model to explain where electrons are located, it really only works for hydrogen. We just use it to show proposed places for all the other atoms as well. Okay, and as we go on, we'll talk about the quantum model of the atom, of what we use today. But from what you understand and what you've been taught in the past, understanding that electrons are traveling around the nucleus in specific patterns, that is what we are using as of right now. Okay, so this is the most widely accepted model that we use. All right, the next thing I want to talk about are isotopes. Isotopes are naturally occurring variants of an element. Well, how do you change an element? Well, there's only really one way that you can change an element without changing it, and that's where you change the number of neutrons. So, for example, hydrogen. Hydrogen has 3 isotopes. It has protium, deuterium, and tritium. Now, one of these makes up most of the hydrogen in the entire universe, most of it. But all 3 of them exist in the universe. Okay, protium is an atom that consists of 1 proton and 1 electron, and that's it. Proton in the nucleus, electron on the outside. Deuterium has 1 proton, 1 electron, and 1 neutron. So in the nucleus there is a proton and a neutron and 1 electron traveling around. And tritium has 1 proton, 1 electron, and 2 neutrons. So it's 3 times heavier than protium because it has 3 of those particles in the nucleus. Now, it's important to understand that an isotope changes an element. These are all hydrogen because they all have 1 proton. They all have an atomic number of 1. But because the neutrons are changing, that's what makes it a different isotope of hydrogen. Okay? If we are also looking at the periodic table, okay, if we're looking at a cell on the periodic table, they typically tend to have certain things written out, and it's important to know what all of these symbols and numbers are. Okay, the whole number in the periodic table box is going to be the atomic number, and like we just said, the atomic number is what represents the number of protons. Okay, always. The symbol is going to be the abbreviation for the element itself, Most periodic tables have the elemental name written out, and then there's usually a decimal at the bottom, and this is the atomic mass. And we'll go more into the atomic mass next unit, but the atomic mass represents the averages of all of the isotopes of that particular element. So if I'm looking at hydrogen, it takes protium, deuterium, and tritium and averages all of them together to get that number, to get that mass. Okay. So a couple of other things that we have something called the mass number. The mass number is the sum of protons and neutrons. In an atom. Now, it usually, when we talk about the mass number of an element, we're talking about the most common. As I told you, protium is the most common form of hydrogen in the universe. And when we talk about the mass number of hydrogen, we're usually referring to that one. So the sum of protons and neutrons in protium is 1 because there's no neutrons. Okay. If I were to look at something like oxygen, the most common form of oxygen has 8 protons and 8 neutrons in its nucleus. So that gives us 16. So there are a couple of different ways to write a mass number. You'll write out the element name and the 16 out beside it, or you can write the elemental symbol with a 16 in the top left superscript portion. Okay. If you are writing the atomic number, is written in the lower left subscript, and you can write them both together. So you can have the mass number and the atomic number both written at the same time. Do make sure you know the difference between those superscripts and subscripts on the left, because eventually we're going to write things that go in the top and bottom on the right side as well. So knowing all those locations is very, very important. The last thing I want to talk about and introduce you to is something called valence electrons. Valence electrons are electrons that occupy the outermost energy level of an atom. So remember, I talked about how Niels Bohr talked about the levels of the atom and how those electrons can move. Well, the valence level, the valence shell, is the outermost level that electrons can go to. Okay, we'll talk more about that as time goes on. But overall, that covers the atomic structure that we need to talk about. Next class, we're going to talk about states of matter and other types and branches of chemistry. Until then, remember, work together, help each other, and make the world a better place. See ya.